cover all the alternative processing, but will be more as an introductory level of introduction. So probably we will not touch too much in depth. Basically, you need to learn how it works and when how to apply the knowledge to understand the mechanism, and that's about it. So our learning objectives for this course. So first one is to compare the conventional processing and alternative processing. And second, you guys will try to classify different types of alternative processing, and then we'll describe the definition, operation, and the mechanisms of them. And also finally, we'll talk about their advantages and disadvantages. So what is alternative processing? Anyone wants to guess? Oh, by the way, if you haven't downloaded your course slides, please go to the Canvas. I just uploaded it 10 minutes before the class. So if you want to take notes, please go ahead, download it. So what is alternative processing? Okay, so let's think about let's look at the conventional thermal processing first. So conventional processing, actually, we're treating our food products directly using heat. Okay, so like blanching, pasteurization, and sterilization. So we're directly using some heating media to increase the temperature of the food so that the pathogens and the enzymes can be either killed or inactivated. So that is conventional. And how about the alternative processing? So before we go to that, let's think about what are the limitations we have. Why do we need to come up with other processing technologies? Since the conventional one is so straightforward. So if we think about their limitations, the thermal processing always causes nutrients and the flavor loss, right? You guys did the lab in the blanching lab, and you can see the color of the green bean that we processed actually changed a lot before and after the blanching. So there's a lot of loss in terms of the flavor and nutrients. And second, it takes a long time. You guys still remember the retort experiment, right? So I let you guys go home during the processing time because it really takes a long time, and it doesn't make sense for you guys to watch the retort, right? Because it's everything is going inside there, and typically a retort process takes more than an hour. That includes the come up time, the holding time, and the cooling time, which is considerably long time. And third, there's a lot of energy required to heat up foods, right? So we use steam, and that the steam generation process is quite energy extensive. And finally, water, right? So in the retort process, we use a lot of water to cool down the can after processing, because otherwise they will be overheated. So all those limitations of the conventional processing. That's why we trying very hard to come up with other strategies to mitigate those limitations. So if we think about the purpose of food processing, there are two purposes, right? So first, we want to transform those raw products into consumer-ready products, right? And the second reason, purpose or goal is to prevent or reduce the negative changes in quality, either by kill pathogens or deactivate enzymes. So a lot of alternative processing, they're targeting on the number 2 goal, which is to kill pathogens or deactivate enzymes. So here I list a few alternative processing. Either they have been commercialized or not. We have microwave, infrared, irradiation, radio frequency, high pressure processing, ultrasound, pulse electric field, and pulse light technologies. I believe there are a few that you can identify, right? So microwave, very common, right? And then the high pressure, probably some of you heard about it. And the rest of them just sounds like unfamiliar. Maybe the irradiation one is one of the familiar one, because this one, the irradiation has been applied for many, many years, but it's more for the industrial production. We in our daily life, we don't see it. And there are very limited locations in the United States that are allowed to perform irradiation. Okay. So we'll go through these technologies today together. And I hope after this class, you have better idea what are they and how they works. Well, so I'm going to start with the microwave, infrared, irradiation, and the radio frequency. Do you guys know why I put them together? Maybe a guess?
They're all using some kind of wave.
Yes, exactly. Thank you, Christine. Yes, they are all electromagnetic waves. So if you look at this figure, you can see that everything other than the visible light can be used for alternative processing. So, which is interesting that any wave that, as long as you can not see it, they have some bacterial killing effect or some other ways to process food. So we have some long waves like radio, microwave, and infrared. Those are very long wavelengths electromagnetic waves. And then on the other hand, we have very short waves, especially the gamma ray is has a lot of energy and the frequency. So and those pictures you can see here, they kind of show you their relative size scale. For example, the radio is can be 1 kilometer in length, and then the smallest one is just nuclear size. Okay, and the longer wavelength, the smaller the frequency, and the shorter the wavelength, the larger the frequency. Okay, so that's probably you have learned it in the physics class, and we'll use all of those physics stuff to process foods. Okay, so long wavelengths and the short wavelengths, they have very different impact on food molecules. So those long wavelengths, like radio frequency, infrared, microwave, they actually can interact with water molecule either by increasing their vibration or rotation or torsion. So you guys learned that all those molecular motion are related to the thermal energy. The more vibration, then probably the higher temperature it is. Right? And then those shorter wavelengths, they will actually causing something called the ionization effect, which I will talk later. Okay? So if we have very long wavelengths, especially the radio frequency, they cause the increase of temperature. So once the temperature is increased to a certain level, the bacteria cannot survive. So that's the long wavelengths electromagnetic wave, how they kills bacteria. On the other hand, those X-ray ultraviolet or gamma ray, those short wavelengths, they actually can interact directly with DNA or protein to cause damage. So it's more like an indirect way of killing bacteria. So let's watch a video about the mechanism of microwave interacting with water, and you guys might have a better idea how that works. Share the sound.
From the magnetron penetrates into the or in the oven where the walls radiate a rise in temperature. In a traditional oven or stove, we heat food by placing a pan on a burner, or in the oven where the walls radiate heat, which cooks the outside of the food. The insides cook when heat transfers from the surface of the food to its interior. In contrast, energy from the magnetron penetrates into the food, which means the whole mass of the food can be cooked simultaneously. How does it do this? Well, our food is filled with water, which is positively charged at one end and negative at the other. To give these molecules more energy, we expose it to electromagnetic waves that emanate from the tube. By definition, the waves have electrical and magnetic fields that change direction rapidly. For this oven, the direction of the fields change 2.45 billion times per second. Water will try to align with the radiation's electric field. The changing field rocks the water molecules back and forth rapidly, and molecular friction from this creates heat as the motion disrupts the hydrogen bonds between neighboring water molecules. Now, you can get an idea of the wavelength of the energy emitted from the magnetron using cheese.
So basically, you guys can see that the frequency of the microwave is in the same range of how water molecule vibrates. So that's why there's kind of resonance that heats the water up, because once the water is heat, because we know a lot of foods, their main component is water, right? So when the water is heated up, the food also heats up. So I always got the question, like, why we cannot put metal like aluminum foil into the microwave. Do you guys know why? What would happen um, if we have metal interacting with the microwave?
It sparks.
Yes. Why do you think it sparks, Christine?
I don't really have any idea.
Doesn't metal conduct heat or something like that?
Yes, metal conducts heat. Do you think water also conducts heat, Alison?
Technically, yes, but I think it's different, isn't it?
Yeah, metal conducts heat faster. Exactly. I saw Vincent. You want to?
Oh, I was just gonna say
Mhm.
maybe because like the molecules are like tighter packed, so it's harder for them to move, so it causes some like friction or something like that.
So you mentioned that the metal has more compacted elements.
Yeah.
Is it okay? Well, that's part of the reason, actually. So one of the reason is that when we apply the microwave to metal, we apply a electric field. And in metal, the problem is that it contains a lot of free electron. And those electron, because metal is conductor, so the free electron, they can move around the different area. And when we apply a electric field there, those electrons tend to accumulate in one side. Um, and that causes very high voltage locally. And that high voltage sometimes just it just generates some fire, and because once the voltage is too high, then it creates locally high temperature, and sometimes it hits through the air and cause a lot of damage. And now another reason is that the metal can reflect microwave. so that will damage the microwave generator. So there are a lot of videos on YouTube that people are heating metals, and then finally the microwave exploded. So a lot of crazy experiments. So this is just something that I want to share with you. One of the fun fact that why we cannot put metal there. And Alice mentioned that metal is a good heat conductor. That's also part of the reason, right? Because once it gets heat very soon, there's no like water, because water has larger heat capacity. Even with the same amount of thermal input, energy input, the temperature increase is more gently compared to metal, right? So in metal, there will be some extremely high temperature in some localized area. So that's also a very important part. I didn't even think about that. Okay, so that's about the microwave. So actually in the industry, we use more of the radio frequency. That's because the radio frequency has longer wavelengths, and that wavelength allows the penetration depth to be deeper than the microwave. If you guys learn about some microwave to heat up your frozen food, you probably will see that the frozen food, um, uh, especially the core, takes a long time to be defrozen. That's because the penetration depth of the microwave is just 2 centimeters, 3 centimeters long. But for radio frequency, we can actually make it deeper by adjusting the wavelengths. So that's the difference. But you can see those equipment, those radio frequency equipment, they are much larger than our home style microwave. So it's quite expensive. So some advantages and disadvantages of microwave and the radio frequency and the infrared processing. Good part about it, it's very fast, right? The microwave takes 30 seconds, 1 minute to heat up food. And if we're using radio frequency, it can be continuous processing, right? We can use the conveyor to send the food products into the machine, and after the processing, it can be coming out. So everything is very controllable. And also we can adjust the heat penetration depth by changing the wavelength. But disadvantages, you can see it's huge equipment, requires a large capital investment, and also it is a thermal process, right? We didn't get rid of the heat. The way that we kill bacteria is to actually to heat them up, right? So that's the advantage and disadvantage of the long wavelength processing. Okay, and then after talking about those long wavelengths, the rest of them are all short wavelengths. And those wavelengths, we call them irradiation. And UV is one of the special one. It's not called irradiation, but sometimes I'll talk later. It's called it's used for pulsed light processing. So in irradiation, actually, we use very high energy of those electromagnetic wave to directly kill the bacteria. And there are two pathways, actually. The first way is to use the direct damage of the DNA or protein, those large molecules, by the wavelength. And the other way is that the irradiation interacts with water to produce free radicals. And you guys learn from general chemistry that those free radicals are highly reactive. So they can easily oxidize the DNA and cause some irreversible damage. So these are two ways for the irradiation that they kill bacteria. and sometimes they happen simultaneously. So some of examples that we use food irradiation in the industry is that we use a very small dose of the irradiation to inhibit the sprouting of the potatoes, onions, and the garlics. And the dose we use is 150 Gary. This is a very small dose because if you guys look at the table here, you'll see that we will need a much larger dose to kill to kill bacteria. For example, if you look at the fresh shell eggs, and if we want to inactivate any salmonella there, we need 3,000 Garys, okay, which is about 20 times greater than the dose that we use to inhibit the growth of the sprouts. And if we want to achieve a complete sterilization, like the retort, in that case, we need 44 kilo Gary minimum. So this is a huge dose, okay? So you can find other doses to achieve different applications, just for your information. Okay. So that's about the food irradiation, and the good part of that is the penetration is good. We can always use that to process those packaged foods, especially canned foods. But it's the disadvantage is that the capital cost is very high because of all the safety regulations, and also because the radiation generates free radicals by interacting with water. And those free radicals, they do not just targeting at DNAs. They also react with the flavor compounds, the nutrients, to cause the extensive oxidation effect. And that's why those irradiated foods usually don't taste that good because there's some fat lipid oxidation going on there to a certain degree. Do you guys have any questions before we move on?
Yeah, I had one just about kind of the longer wavelength ones.
Mhm.
So when you take like a microwave and then you like scale it down to like a longer wavelength, but like having like less energy in it, to maintain that sort of like short residence time, are they increasing the intensity of the wave? Or
Exactly, Chris. Yes. So you know, for wave we have like two parameters, right? One is the frequency, right? Basically is how fast the wave change direction, right? And then the other parameter is the intensity, basically what is the height. For example, if we have light, we have two parameters. One is the wavelength, the color, right? And then the other one is the intensity, how strong is the light. So basically those two parameters can both be modulated or controlled by the equipment. So if we use radio frequency, although the frequency is very low, but we actually provide a very high intensity to kind of compromise that amount of energy. Does that answer your question, Chris?
yeah, and then I was also curious about like when it comes to use of such equipment, is there special like safety precautions for either radiation or the shortwave or
Yeah,
long
the
wave?
shortwave one, yes, there are a lot of safety regulation, and we'll cover that in the 474 bit because that's more specifically designed for heavily introducing the non-thermal processing, and this class is more like giving you a very broad view of how these techniques looks like. So so those will not be covered that much in this class.
You had said for the longer wavelength processes that
Mhm.
that could be a continuous process. Does that not cause issues with the waves coming out of the machine if it's
That's a
open to
good
let the product go
question.
through?
Yes, I think that's a good question. Um, actually, I didn't look into how they contain the wavelengths, but um, um, for those electromagnetic waves, we can use either magnetic field or electric field to control their pathways. But that's a good point. How do they contain it within the equipment? Um, but it would be, to me, it seems like the production rate and the yield and all the production complexity will be drastically decreased if they can design it into a continuous process. And you can see it's because everything is on conveyor and it doesn't seem like to be batch processing, not like home style microwave. I guess that's why the equipment has been built in such a large size. Okay. Any other questions before we move on? Okay, so all right, so the next one is the high pressure processing. So the high pressure processing actually is getting a lot of attention in the past 20 years. It was firstly developed in 1990s, and it was found to very helpful to process seafoods and fruits juices without causing much nutrition loss. And it's hard to make it into a continuous process because we're applying a lot of pressure, but it's more like a semi-continuous process. For example, if you guys look at this figure, you can see that the unprocessed food will be placed into a container into the vessel, and then the vessel will be loaded into with water, and then after water is filled, we can apply a high pressure by pressing the water. And afterwards, we just drain the water and take out the food. So it's like, it's semi-batch processing, but it's kind of mixture of batch processing and the continuous processing. And the pressure that we apply is about 200 to 1000 Pascal. And they will be exposed for just a few minutes, okay? And then using the pressure transmitting fluid, such as water. So the fluid, the purpose of fluid is just to kind of convey the pressure to the food product. So this is how high pressure processing works. And the way that the pressure can kill bacteria is that they can disrupt the cell membrane. For example, this is an image showing that the mechanism of bacterial control and inactivation using listeria. And you can see so typically it's a combination of process of breakdown of the non-covalent bonds in large macromolecules, and also has some biochemical effects and even some genetic mechanisms. And you can see the cell membrane actually change a lot, right? Deformed a lot after processing. And there's a video show as a demo of a company that processed the fruit juice using high pressure processing.
The unique appearance, flavor, and vitamins of fresh fruit is one of the most important bases of a healthy lifestyle. How can we maintain these valuable characteristics without using any kind of preserving agents or chemicals? ThyssenKrupp Uhde High Pressure Technologies, using pressure to preserve food gently and efficiently. Pressure of up to 6,000 bar denaturalizes pathogenic germs like Listeria, E. coli or Salmonella, and fungi. As food is processed in the final packaging, the high-pressure processing meets maximum hygienic requirements. After being loaded into special baskets, the final packed product moves into the vessel. Then the vessel goes into process position. It is closed by lids and filled up with potable water. Just for a few minutes, water pressure increases up to 6,000 bar. The product will maintain its pure and biological state because no additives, except energy and pure water, are used. Nevertheless, it is not heated up. Taste, flavor, vitamins, and appearance remain unaltered. The process leads to a 10 times longer shelf life. Customers require pure, natural, and fresh products due to a worldwide increasing trend for healthy eating. Uda's high-pressure preservation using pressure up to 6,000 bar offers great opportunities to meet this trend. The method is well proven, especially for vegetable, fruit, fish, dairy, and meat products.
Isn't that looks cool? So you can see especially it's fun, you see that those bacteria, they're squeezed to death, right? So this is kind of demo, but in fact, we know that it's not squeezed, right? It's just changing the permeation of the membrane so that they kind of go through a correlation process to die. Okay, so some advantage and disadvantage of the high HPP process. So there's a minimal effect on flavor, nutrients, and pigment compounds because we didn't apply any thermal treatment there. Actually, when we press it, the water, it generates a certain amount of heat, but we can always modulate the temperature, right? By something like a water bath or some other technique to minimize that. So there doesn't necessarily have to be any temperature fluctuation. And the second, the texture loss is also minimum, okay? But the equipment is very expensive, and also the operation cost is also very high because applying a large, such a huge pressure, remember it's about 200 millipascal, costs a lot of energy. And also we need energy to load water and drain water. Although the water can be recyclable, they're just working at the pressure transmitting fluid. They can be recyclable, but we have to to drain it and to pump it. So that also costs some energy as well. So that's HPP. Okay, so the next one is the ultrasound. Ultrasound is quite different from those previous ones that we have seen. All those previous techniques that we discussed, they are all commercialized. But ultrasound is one of that technology that was developed a long time ago, and the scientists have tried very hard to commercialize them, but very hard. So by definition, ultrasound, it's basically they are very high frequency of the sound wave, okay, and they actually are considered it's considered as both thermal and a non-thermal treatment because during the ultrasonication process, we are generating some localized high heat and also localized high pressure. And this is how the ultrasonic process looks like. And you can see the probe is kind of small. That's part of the reason it cannot be commercialized, right? Because it's every probe we have to align a lot of probes in the production line, and that's very that costs a lot of money. And also when the probe is used, it's actually damaged in a very fast rate. For example, a typical probe that we use in experiment, they are damaged within I would say 100 hours of use if we apply them to like a big amplitude of the wavelength, the wave intensity. So we have to replace the probe very frequently, and also the wavelength does not necessarily distribute evenly in a spatial distribution. So that's also part of the reason that it's hard to be commercialized. So the mechanisms of ultrasonic processing is that they actually create bubbles by cavitation, and those bubbles will grow in the liquid. And once they collapse during compression, it will create a huge mechanical shocks, and that will disrupt the structural and functional components of cell, especially those bacteria, and then they ultimately lead to the cell to die. And also, when the bubble they explode, they actually generate the zones of highly localized or extreme pressures, even greater than 10 to 8. This is a mistyping. This should be 10 to 8 Pascal. So think about our atmosphere pressure. It's 10 to 5, right? So it's about 1,000 atmospheric pressure, and the local temperature can goes to 4,000 K. Although it's very small region, but it's very high temperature in very tiny spot, and those will disrupt the cell structure and inactivate microorganisms. So very promising technique, okay? And typically during ultrasonic processing, we need to use ice water baths to make sure the temperature fluctuation can be controlled, because otherwise the liquid will absorb all the energy just that is released by the ultrasonic processing, and the temperature will be elevated in a very short time. Okay. So one of the example of the ultrasonic processing is that we use the ultrasonic bath to wash fruits, but this is only happening in labs because it's never commercialized. It's one of the techniques that people are trying very hard to commercialize, but it's always difficult, especially in the industrial scale. Any questions before we move on? Okay, all right, so advantages and disadvantages. Good thing is that ultrasound treatment is very effective against those cells, okay? Because those cell membrane, they're very sensitive to those high intensity ultrasonic waves. But and also we can easily add a ultrasonic probe into any processing plant. For example, if you are doing a radio wave, for example, radio frequency processing, and we can just add a probe there, right? And it doesn't require much of the rebuilding of the equipment. Right? So ultrasound is usually combined with other treatments like UV or sometimes microwave. So those can be combined, but although they are not commercialized, but we see a lot of experimental studies, publications in that area. But disadvantages, as we talked a lot about challenges of scaling up, especially the probe is so sensitive, and their usage life is so short. We have to change it every 100 hours, and they cost hundreds of dollars. So that's one of the issue. And also they also cause textual changes, especially if we have something like cheese or ice cream, those initial structure of the food will be disrupted completely by the ultrasound because it's too powerful, and they're actually mechanical waves if you think about it, instead of electromagnetic waves. So those mechanical waves can cause damage to the food structure. Okay, so the next one is called pulsed electric field processing, and it's in abbreviation, it's PEF. So pulsed electric field processing involves the application of high voltage pulses, so that we will apply a series of electrode pairs, and then there will be high voltage applied to there. So there will be a current flow to go through the food. For example, you can see here, we can use it to process flowing milk, right? And then you can see there are two sets of the electrode pairs. And we usually use a very high voltage, 20 to 80 kilovolts per centimeter. So when we talk about the electric fields, it's always by unit distance. Okay? So this is a very good continuous process if it works well, right? And we don't need to apply too much heat. So actually the application of the PEF has been explored by some companies, and they actually apply a very, very short electro pulse, like 1 to 100 microsecond, okay? And there will be some lethal effect. Although the mechanism, even to date, is not fully understood yet. So there are some assumptions, basically. Some people think that it's due to the formation of the pores on the cell membrane. So one of the hypothetical diagram, it's a little bit vague here, but you can see that once the cell is exposed to the high electric field, the electrons will have very uneven distribution on the cell membrane, and that will cause some the membrane to break, right? Because if you have the very high voltage difference, that will disrupt the cell membrane, just like a pH differences inside and outside the cell. So this is how people think how it works, but it's still not confirmed yet because it's hard to do experiment and to measure the electron distribution within such a short time period. That's why it's never confirmed. Okay, so here I have an example of one European company developing this technology to process foods.
Fresh, our olive oil, extra virgin, our cider, aromatic, and there is an electrifying new technology that can make those easier to produce and healthier.
Apple farm in Care, Ireland produces 600 tons of apples a year. A quarter of the harvest is processed into juice, cider and vinegar. This family-owned farm has joined a European research project to improve food processing using a pulse electric field.
The ideal conditions to use this in are when we have hard apples, so apples that are not very long picked, maybe the first few weeks after harvest, and when we put them through this process we get an increase in yield of maybe 3 or 4%.
Electric pulses in the treatment chamber perforate the fruit cells, making juicing easier. A modification of the same technology can also be used to kill microbes and increase the shelf life of fresh juice.
We're waiting for a smaller chamber to come so that we can apply a greater charge in a smaller area, and when we do that we're hoping that we will not only split open the cells of the fruit but also much smaller cells like bacterial cells and so on.
PEF isn't just about apples. This lab at the University of Zaragoza produces red wine from grapes processed with PEF. By creating pores in their skin cells, PEF shortens maceration time without affecting the taste.
There's a change in polyphenols. For that reason, you can see that the wine processed with PEF has deeper color, has more polyphenols than non-processed wine.
The researchers now want to showcase PEF's commercial advantages to food companies. Initial investments in the technology could be reduced as cheaper generators are developed. Best of all, running energy costs are surprisingly low.
The process requires high voltage, but the treatment is applied as very short pulses, the microsecond scale. That's 1/1,000,000th of a second. So the total energy requirement is very small. Treating a kilo of tomatoes requires less energy than heating 1 liter of water by 1 degree.
Tomatoes processed this way are easily peeled without using boiling water. That saves energy and helps the environment. PEF technology also preserves the nutritional value of vegetables, meaning the food industry can produce processed food that's tasty and healthy.
Do you think these results will be convincing for the industry to start embracing this technology at a wider scale?
This is a non-heating technology, so it avoids negative effects of heat on food makeup. So the consumer will receive products with better sensory qualities and more nutritional value. Furthermore, this reduces energy costs in the processing.
Por otro lado, permite reducir los costes energéticos del procesado.
Researchers say that pulse electric field technology is particularly.
So that's about PEF. Isn't that sounds cool? Well, it's still in its quite early stage, but you can see it's probably also difficult to scale up, right? Because it's so difficult to control the electric field, and when it's scaled up, it's it's going to be quite difficult. So some advantages and disadvantages. So like ultrasound, the PEF is also very effective against those cells because they can damage the cell membrane very accurately. So it requires extremely short processing time. And energy is also efficient. I didn't list here, but the energy is also very efficient, right? You can think about all the energy is used to kill bacteria. Not like if we're thinking about conventional processing, first we use the energy to generate steam, and the steam will be used to heat up foods, right? And then the foods will be cooled down. So that every step is just the purpose was to kill bacteria, but a lot of energy waste during those process. But here PEF, almost all the energy is used to to kill bacteria. But for disadvantages, it's not suitable for non-liquid foods, right? Because we need the water to be used as the conductor, right? To pass through the electrons. And it's less effective against the enzymes and spores, right? Because enzymes within this short amount of time, because enzymes they are proteins, they're too small to be affected by the electrons. And the spores sometimes they are because they are not complete microorganism. They don't have the membrane to be destroyed, right? And also the scaling up, it's very difficult. But there are companies working on it, and hopefully we'll see some commercialized product of PEF in the future. I think PEF, compare-wise, is closer to ultrasound, because for ultrasound, I think people worked on it for many years, and none of them was able to commercialize it. Okay, so the last one is the pulsed light technology, and this one is much more newer compared to PEF and ultrasound. So pulsed light technology is an innovative method. Basically, it can be used to decontaminate and sterilize foods by very high power, okay, and a very short duration of pulse light. So typically we use inert gas flash lamps to emit light, and the exposure of the PL on the pulse light can be regarded as a form of UV light. Although we are emitting white light, but the only efficient or useful part of the light is the UV part. Okay, so the white light actually only contains 25% of UV. Okay, so once the UV is emitted, that portion will result in the microbial inactivation. It will be done through several pathways, either photochemical, photothermal, or photophysical routes, just like our UV disinfector. You use a lot in those hospitals, other hygiene process, and for the pulse light, it's very similar to the PEF, that we only apply light for a very short period of time. For example, the pulse light it will be applied at 1 to 20 pulses every second. Okay, so basically 1 second will be very fast to kill the bacteria. So because there are very limited information about pulse light, probably I'm just introducing it to you, and you guys don't have to think about either what are their how are they applied to foods, what are their advantages, disadvantages, because it's too new to the food industry. Okay. Okay, so here, after we talked about so many techniques, I want to summarize them into a table so you guys can have a better idea when it comes to comparison. So the first one is the high pressure processing, right? This one probably you guys are more familiar with. So we can control the processing time and also the pressure, right? And the advantage is that we can best retain those flavor, nutrients, and pigment, and minimize the textural loss. But the equipment is very expensive because to generate such a high pressure is not easy. And you guys watch a video that the company, they use the high pressure processing to produce the orange juice, right? And everything is actually in a bottle, it's pre-packaged. And because it's so expensive, usually we use it to produce high value added products like seafood and meat, okay? And then the second one is the pulsed electric field, or PEF. We can control the electric field intensity and the electrode design, like the shape. So advantages, it's very good to kill bacteria, very sensitive to this electric field, and it only requires very short processing time. But if we are processing a non-liquid foods like beef jerky, like meat, it's very difficult, right? We need some good conductor, and it's not effective against enzymes, right? So if we want to inactivate those browning enzymes in apples, it's not possible, okay? And also the scaling up is very difficult. Okay, so the PEF is used mostly for liquid foods, okay, like fruit juice and milk. Ultrasound is more used in lab, but not commercialized. we can control the amplitude of the ultrasonic wavelengths, and also we can change the exposure time. And the advantage is very good for killing bacteria, but it's very hard to scale up, and also it causes damage to the food texture and the food matrix. Okay. And ionization radiation is frequently used for a lot of foods, either to control bacteria or control the pest. We can adjust the dosage and the exposure time to achieve different goals, like inhibit the sprouting, kill bacteria, or achieve a complete sterilization. Good advantages is it gets very good penetration power, so we can use it to process packaged foods. But because radiation is so dangerous, the capital cost is high to ensure the safety, and also because the ionization effect can generate a lot of free radicals. So those free radicals can cause some damage to lipids and other flavors, to cause some off flavor issue or other oxidation problems. And ionization radiation can be used for a lot of fresh produce like meat, vegetables, and a lot of canned foods. And last one is the microwave infrared radio frequency processing. They are very similar. They use long wavelengths, but we can change the intensity and exposure time wavelengths to control their penetration depth and their degree of heating. They require very short residence time and can be continuous processing. But the problem is that they are thermal processing, right? So basically we're heating them up using some other energy and to kill the bacteria. And there's also unnecessarily some nutrition loss associated with the thermal processing. So these are the comparisons of all the techniques that we have learned today. So finally, I want to bring a discussion session, kind of refresh our mind which of them are thermal processing and which of them are non-thermal processing. And I was planning to put you guys into breakout groups to discuss about this, but we are probably a little bit late today. And also, I think this question is a little bit straightforward. You guys might can figure out quite easily, right? So microwave, thermal, non-thermal? It's thermal, right? And the infrared is also thermal. Irradiation, non-thermal, right? It's directly killing bacteria by damaging the DNA. Radio frequency is also thermal, right? So those three, long wavelength, they're all thermal. And the rest of them, the high pressure processing is non-thermal, right? Ultrasound, it's mixed thermal and non-thermal, right? There's the mechanical damaging, but on the other hand, the cavitation process also cause locally high temperature. So it's considered a combination of thermal and non-thermal processing, right? And the pulse electric field, because the treatment time is so short, right? So it's more like a non-thermal. And pulse light, it's also because of short treatment time, right? It's also a non-thermal processing. Okay, so a brief summary of this class. So we basically learn about the differences between the conventional processing and alternative processing, right? And then we talked about the different alternative processing. We talked about 8 technologies today. and their definition, their operation mechanism of them. And finally, we covered their advantages and shortcomings, and some of them have case studies, some of them don't. Right. So basically, that's all about our lecture today. Do you guys have any questions before we finish? Yes, Chris.
In terms of use, say outside of like industrial needs, because I know that when they were talking about PEF, that it was like you could produce like a very peelable tomato in very little time compared to like boiling them, which is like the usual thing used in kitchens today.
Right.
So do you think that that is something that could be used in like more culinology applications in the future rather than just solely in food science?
Oh, Chris, that's a good point. Culinology, yes. If it's a small scale, then it's, yeah, we can probably make some home style, small scale PF processor, just like a home style ultrasonic vegetable cleaner, right? So that's a good way of commercialized in small scale. Good idea. Yeah. Is there any product like this already in the market? I think it's a good to some good information we can look into after class. I saw Alaya, you have a question? Okay. Okay. Any other questions before we finish? All right. So that's it for today. Thank you guys for your hard work this entire quarter, and I'm glad that we have gone through everything. And thank you for all the support. And if you need any help to prepare your final, you can always schedule a appointment with me tomorrow, because tomorrow is the last day, right? So the final will be posted on Monday. Feel free to take it at any time. And don't miss the due days. We have 4 dues this Sunday night, okay? All right, thank you guys. And that's it for today's class.
Thank you. Bye.
Thank you.
Thank you.
Thank you.
Thank you. Have a good one.
Thank you.
Thank you.